Okay, so welcome to the latest edition of the Pangolin Seminar. Today it's our great pleasure to have Lorenzo Ruffoni from Tufts University. Is that correct? My pronunciation.
Yes, that's correct.
Who will talk to us about strict hyperbolization and spatial cubulations. Over to you, Lorenzo.
Thank you very much, Andrea, and thank you very much for the invitation. Let me share my screen. All right, here we go. Can you see my slide? Okay. All right, so again, thank you very much for the invitation. If you have any questions during my talk, feel free to unmute yourself or write in the chat. I should be able to follow that. So today I'm talking about a joint project with Jean Lafont, which is about two procedures in geometric group theory / geometric topology. And these procedures are strict hyperbolization and spatial cubulation. So let me give you like a 2 minutes preview of what the talk is about before getting into the details of that. So strict hyperbolization is a procedure that people use and have used to construct negatively curved groups. Let me give you the definitions of that. But you should think of these as some discrete groups that somehow resemble hyperbolic geometry, have features of hyperbolic geometry. On the other hand, spatial cubulation is a procedure that people have used and used to construct subgroups of GLNZ. Okay, not the most straightforward way of constructing groups of matrices over the integers, but one of the things that you get out of a spatial cubulation is a subgroup of matrices over the integers. And the result we proved with Jean is this theorem. That many of these negatively curved groups that you get from strict hyperbolization are subgroups of GLNZ. So you should think of this as a sort of regularization result. You start with something which is a negatively curved group and can be quite pathological, and I will say more about that. And it turns out that your group is just a group of matrices over the integers. Okay, so here's my outline for today. I will start with some motivation and history of where these words and questions come from. And then I will give you a quick review of these two constructions, hyperbolization and cubulation, and then give you a sketch of what we've done. As a standing assumption for my talk, all my manifolds are connected, closed, orientable, so no boundary in particular, and all my groups are finitely generated unless they are obviously not finitely generated. All right, so let me get started. I'm trained as a surface guy, so by contract, I need to start all of my talks with donuts on my slide. So here's my first slide. This is supposed to be a table for the classification of surfaces. So classification in terms of topology, geometry, and algebra. So topology of surfaces, there's not much to say. So you either have genus 0, the sphere, genus 1, torus, or genus 2 or higher number of holes. That's how we divide surfaces into 3 families. As far as the geometry of them is concerned, well, genus 0 is what we call spherical geometry. So that's a model for the sphere. Genus 1, this is where flat geometry or Euclidean geometry occurs, and we think of that as flat geometry, curvature 0. And as soon as you have 2 or more handles, genus, you are in the kingdom of hyperbolic geometry, negative curvature. And I will say more about that in a second, but let me just also do the algebra first. In terms of the fundamental group of these spaces. So for the sphere, the fundamental group is trivial, and indeed, I will not think about spherical stuff very much in my talk, so let me just cross it out. We're not going to think of that. And then genus 1, fundamental group is Z2. You can take these two loops as elements that generated the fundamental group, and they commute. So that's your favorite basis for the fundamental group. And then for surfaces of higher genus, the fundamental group is more complicated. I could write a presentation for that, but that's not what I'm interested in. The thing I want to observe is that it's very far away from being abelian, meaning, for instance, it does not contain any Z2 subgroup. All right, so let me say a few more words about the geometry, Euclidean versus hyperbolic. That's something I'm going to be interested in. So these are pictures of the Euclidean plane and hyperbolic plane. and just how to obtain surfaces of genus 1 or higher genus coming from there. So for genus 1, for instance, one way to construct a torus is to take a flat square and then impose some identifications on the boundary. For instance, I'm going to glue the blue edges together, and I'm going to get my toilet paper roll, and then I'm going to also glue the top and the bottom edges together, and that gives you your donut. And then you can also take this square and then propagate the square all over the plane using an action of Z2 by translations, and then that's how you get your tiling of the Euclidean plane by unit squares. And that's a model for the universal cover from the Euclidean plane down to the genus 1 surface. One thing I want to observe here is that if you fix a base point and then you just move the base point around with these translations, so you get all the vertices of this tiling, that gives you a way of embedding Z2 inside E2 in a geometrically meaningful way, meaning that it's like a discretization of the Euclidean plane. And in this sense, we say that Z2 is quasi-isometric to E2, and we say that Z2 is like a group with intrinsic Euclidean geometry. If you do the same thing over to the right, this is a picture of the hyperbolic plane, and of course the arcs of circles that you see are supposed to be geodesics for the hyperbolic metric, so they meet the boundary orthogonally over here. You can play a similar game by taking a fundamental domain, an octagon in this case, over here, and then you impose gluing on the edges. So again, I'm going to glue the blue edge to the blue edge with some hyperbolic isometry, and then the red edge to the red edge, some hyperbolic isometry, and so on, and I get my genus 2 surface in this case. I can move my octagon around using hyperbolic isometries. Let me embarrass myself trying to sketch that. So we're going to pretend that these are copies of the same octagon that go off to infinity. Of course, the picture is super messy because I'm embedding Euclidean, the hyperbolic plane on my Euclidean slide, but I hope that you get the idea. You get the tessellation of H2 by octagons. And again, if you fix a base point and you move that base point around with the groups of transformation, you get a collection of vertices in your tiling, and those are like a natural way of embedding the fundamental group of the surface inside H2 in a geometrically meaningful way. So in this sense, we say that the fundamental group is a hyperbolic group, has features of negative curvature. Something I want to emphasize about this phenomenon in genus 2 is the following uniformization phenomenon, which we can see at the level of geometry, saying that if a surface has a metric of negative curvature, then actually that surface can be realized as a quotient of the hyperbolic plane. Right? So you start with something that has some maybe variable curvature less than 0, and it turns out that your surface is homeomorphic to a hyperbolic manifold. So a quotient of hyperbolic plane. At the level of algebra, so the level of the fundamental group, when your surface has a fundamental group which is far away from being Euclidean, maybe far away from being abelian, then automatically your fundamental group sits inside the group of isometries of the hyperbolic plane. So again, a kind of regularization phenomenon for surfaces, and which is beautiful. And one can ask, well, is this just for surfaces? Does it extend to higher dimension? What's the picture here? How powerful is this hyperbolization idea? Well, in dimension 3, it also works. That's essentially the content of geometrization. If you have a 3 manifold which is hyperbolic enough, then it's actually a hyperbolic manifold. And that's work of Thurston, Perelman, and many other people. But from dimension 4 and up, the picture is very different, mainly for 2 reasons. First reason, we don't quite know how to construct hyperbolic manifolds. That's kind of an overstatement, but constructing hyperbolic manifolds in higher dimension is not as easy as constructing hyperbolic manifolds in dimension 2 and 3. Moreover, there are examples of manifolds of curvature less than 0. So we talk about sectional curvatures less than 0, which are not hyperbolic manifolds. They're not homeomorphic to quotients of hyperbolic space. They could be quotients of some other symmetric space, for instance, a complex hyperbolic space, or they could be branch covers of these. But they're not homeomorphic to genuine quotients of hyperbolic space. So this is suggesting that in higher dimension, in the world of negative curvature, hyperbolic geometry is not spread out as much as we would like, as much as it is in low dimensions, which raises the question, how wide can negative curvature be in higher dimension? What kind of objects do we get when we look at negative curvature in higher dimension? And from the group theoretic point of view, we can make this question more precise. This is a question of Gromov, which is asking if all hyperbolic groups are residually finite. And this question is open before my talk, and also after my talk, this question will remain open, but that's kind of a motivating question in the background of our project. All right, let me a quick review, maybe definition of what I mean when I say curvature in all these contexts. I'm talking about curvature of manifolds on groups. So let me be a little bit more precise on that. So the concept of curvature I'm talking about is something that makes sense in any metric space. So in any metric space, you take your favorite 3 points and you connect them with geodesics, and that gives you a geodesic triangle. And then you look at what kind of triangle you obtained. If it's something that looks like a Euclidean triangle, you say that that's a flat or Euclidean triangle. If it's something that looks skinnier, so something that looks like a triangle in hyperbolic plane where the geodesics bend inwards towards each other, or even more like something that you see in a tree, so like a tripod, then in this case, we say that the triangle is negatively curved, that has some hyperbolic feature. And in the following, I will say that whatever is curved like the hyperbolic plane or all the way to a tripod that has skinny triangles, I will call that negatively curved. And for simplicity, I will use the terminology of calling that space cat -1 or locally cat -1 if this condition is only local. If I have overall something that shows some negative curvature features and maybe somewhere some flat behavior, then I will call that non-positively curved or cat 0. Okay, so essentially what I'm trying to avoid with these definitions is that I don't want fat triangles. I don't want the kind of triangles that we see on a sphere. I'm trying to get rid of that. So examples of things that have this behavior include Riemannian manifolds of sectional curvatures less than 0 or less than or equal to 0. So these would respectively be the cat -1 or cat 0 situation. So again, the difference between cat negative and cat 0 is that you allow some flat behavior in cat 0. For singular spaces, again, trees are examples of cat -1 spaces, so in particular cat 0. And more generally, higher dimensional cell complexes like cubical complexes. I will talk a lot about cubical complexes with some conditional links that ensures that you have negative curvature. So here, like some examples, I should say in my talk, whenever I say cubical complex, I'm thinking of a complex built out of cubes in the same way you construct a simplicial complex out of triangles and tetrahedra and so on. So cubical complex is the cubical analog of that. And I'm going to agree that every cube in a cubical complex is declared to be isometric to a flat unit cube in Rn. So it's just a bunch of flat unit cubes glued together along their faces. So let's have a look at the one in the middle, for instance. This is a flat square from the Euclidean plane. A triangle in there is just a flat triangle that's showing flat curvature. What if I take a triangle that goes over a bunch of faces? Well, again, that's just a piece of the Euclidean plane. Nothing interesting is going on. So that's very flat. Over to the left, those are 3 squares glued together. They're supposed to look like the corner of a cube. So if you look up in your room, in the corner of your room, that's the kind of configuration I'm talking about. So let's look for triangles here. Well, again, if I sit inside one cube, that's just a Euclidean, inside a square, that's just a Euclidean square, I see a flat triangle. But let's look at this big triangle over here, connecting vertex to vertex along the diagonals. So this is a geodesic triangle here, and here, these angles are 45 degrees. So overall, the angle that you see here is an angle of 90 degrees. So you have 3 angles of 90 degrees. That's definitely a fat triangle, much fatter than what you get in Euclidean geometry. So this is something of positive curvature. And again, I don't want that. Over to the right, I have 6 squares coming together. So again, if you look inside a square, that's just usual Euclidean geometry. Let's look at this big triangle here. I'm going to try to connect these 3 points. Now, let's look at the top 2 squares. Those are, each of them is isometric to a Euclidean square, and they're glued together along an edge. So intrinsically, that part of my complex just looks like a pair of Euclidean squares. And if I want to go from one point on the boundary to one point on the boundary, the geodesic goes along the boundary. So here, this is what the geodesic looks like between those 2 points. And of course, same for the third point. So here, this triangle is super thin. It's just a tripod. So this triangle looks like the triangle that you would see in a tree. So this is definitely something of non-positive curvature. You see, it's not on the nose negatively curved because we have a lot of flatness going on inside the interior of faces, but overall, this is non-positively curved. And finally, to bring the definition to the groups, if you have a group which acts on a cut K space, you say that the group is cut K itself, provided that the action is geometric, meaning that the action is by isometries, it's compact and proper. So it's an action that makes sense with respect to the geometry. All right, any questions before I switch to my second chapter?
No, I think it's very clear. Apparently, okay. No questions.
Okay, great. So let me switch to my second chapter. I want to talk about hyperbolization procedures. So hyperbolization procedures is a family of procedures first introduced by Gromov, and then people added their own versions of that. It's a bunch of procedures that you should think of as kind of machines with an input and an output. So the input is usually a cell complex. And for my talk, this cell complex will always be a cubical complex, but other procedures you can input a simplicial complex, for instance. So you put that into your machine, and the output is some space that I'm gonna call X sub hype, which is a cut K space. And here maybe I should say locally cut K, but then you take the universal cover to get globally cut K, and here K can be, so as before, can be a space of non-positive curvature or a space of even negative curvature. Well, the most stupid way of doing that is you give me a cell complex and I give you hyperbolic space. That would be a hyperbolization procedure, but not very interesting because it doesn't at all engage the kind of input that you provide. So the smart hyperbolization procedures, they all look like something like that. This is the recipe for all of them. You start by cooking up a hyperbolizing cell, which is some space that has some features of hyperbolicity that you want to have in your construction. And then you go in your cell complex and you replace every n cell with a copy of the hyperbolizing cell. Okay, so it's a game where you go in your cell complex and just replace every cell with a given building block. So different hyperbolization procedures differ for what you can input and what kind of replacement you do, what hyperbolization cell you use. I want to talk about two constructions today. One mainly because it's easy to see, and then the second one is actually the one we have worked in. So the first construction is due to Gromov. I call it a weak, this is just my terminology, not at all standard, weak hyperbolization because it gives you, as an output, it gives you a cut zero space. So it gives you a space which is non-positively curved, but not necessarily negatively curved. That's just unfortunate. These procedures are called hyperbolizations, even if the result is not hyperbolic, but just this is the name that Gromov gave them and just stuck around. So we just have to deal with that. So here for this construction, the hyperbolizing cell is a Möbius band over here. And I need you to think about the Möbius band as being a square complex. So let me subdivide my Möbius band into a square complex in this way. So I have 4 vertices, 1, 2, 3, 4, 5, 6 edges, and 2 squares. This is a square in the front. And then the other square is in the back. The picture on the right, I'm just redrawing the same Möbius band in a way that highlights the structure of the boundaries. So let me do that. So say I want to start with this vertex over here, and I walk along the boundary. This is the red edge. I'm going to switch to blue, walking over and down. This is the second edge, so I'm coming down here. Let me switch now to pink. Keep walking along the boundary of my Möbius band and over. And what am I left with? Let's do dark green. Last edge to go back to the beginning, and here I am. Okay, so the boundary of this Möbius band is subdivided as a square, and then the two-dimensional square are kind of wrapping, like the green one is between red and pink, so that's kind of what it's doing. So you glue in this two-dimensional cell between red and pink with a twist, right? Because we're doing a Möbius band, and then for the blue one, that's in the back between blue and green. All right. So I'm doing this to emphasize that in this sigma 2, this hyperbolizing cell that I will use, the boundary of that can be naturally identified with the boundary of a two-dimensional square, and which means that I can run the procedure as I promised by taking some complex, like here I have X is my boundary complex for the three-dimensional Euclidean cube, so topologically this is a sphere. I can go in and remove all the two-dimensional squares I see and just glue a copy of the hyperbolizing cell. Okay, let me do over to the right so it doesn't get messy. What I'm doing here is I'm replacing every square with a copy of this Möbius band. Okay, and same also in the faces in the back. Here the hyperbolization of this complex is some surface, which is kind of a connected sum of 6 RP2s. So up to a finite cover, this is a surface of higher genus. Okay, so this is something that, thanks to low-dimensional magic, is in some sense negatively curved. Like it's the fundamental group has an action on the hyperbolic plane. But let me look a little bit closer to what kind of metric we are putting on this object. So back into the Möbius band here, we want to emphasize that you have right angles at every vertex. So if I look at the right hand side here, this is a right angle, this is a right angle, right angle, right angle, and so on. So when you glue that into the picture, you see that at the vertex here, you have right angle, right angle, right angle, right angle, right angle, and right angle. So you have 6 times pi over 2. This is 3 pi over 2, which is more than 2 pi. So the kind of metric that you have on this space X hyperbolized is something which is flat all over the place, right? These are copies of Euclidean squares, the green and blue membranes, those are completely flat. And then there are 8 vertices where the curvature is concentrated and it's very negative. So overall, this is non-positively curved, if you want, locally cut 0. Starting from something that was a cubulation of a sphere. So here the angle was, in each vertex, was 3 times pi over 2, which is less than 2 pi. So this was positively curved. So in this sense, this is a hyperbolization. It starts with something which is almost everywhere flat with a lot of positive curvature concentrated in vertices, and it gives you something which is almost everywhere flat with lots of negative curvature concentrated into the vertices. And it turns the trivial group into a hyperbolic group. All right. What maybe you dislike about this construction is that it doesn't give you something for which the metric is negatively curved, and it has introduced a lot of non-orientability in the space, which is of course not super desirable. Second example, this is the one that will be more relevant for my talk. This is due to Charney and Davis, and I call this a strict hyperbolization, or they called it a strict hyperbolization to begin with, because the output here is going to be actually negatively curved. So in that sense, it's strictly negatively curved. So again, to define the hyperbolization, I need to give you the hyperbolizing cell. In this case, the hyperbolizing cell is constructed as follows. You start with a hyperbolic surface that has 2 geodesics, which are orthogonal to each other and dual, meaning that they meet just at one point and they meet at that point orthogonally. And then you cut along the red geodesic, you open it up, and then you cut along what is left of the blue geodesic, and your final product is this hyperbolizing cell, which is a hyperbolic surface with boundary and corners. So the boundary is a union of 4 geodesic arcs meeting at orthogonal angles. So again, the thing I want to emphasize is that the boundary of this thing is isometric to the boundary of a square. And then inside you have hyperbolic geometry. Like here, all your triangles inside here are thin. So we can play the same game as before and go inside a square complex and replace every square with a copy of this genus 1 surface with boundary. And that's kind of what it looks like. So here I'm starting with my, again, X is my cubulation of a sphere. And I go and replace every square with a genus 1 surface constructed as above. And my result, X hyperbolized, this is topologically a surface of genus 6. So again, this is a surface of higher genus. In some sense, this is a negatively curved object, at least as far as the fundamental group is concerned, by some low dimensional magic. Let me once again have a closer look at what kind of geometry we have on the space. Again, here inside each of these hyperbolizing cells, I see hyperbolic geometry. Triangles are thin. However, I was starting with something with positive curvature at vertices, and that doesn't change here. So just as a caveat, in both cases, you have at the corner 3 times pi over 2, which is less than 2 pi. So you have some positive curvature at the vertices. But on the right-hand side, you have enough negative curvature everywhere else that makes overall the object kind of negatively curved. It's not cut 0 or cut -1 because of these points, but it has features of negative curvature. So the suggestion is that if you start with something that has links that don't do that, it doesn't have points that do that, meaning all the links are large enough, then you should get something that does not do that in the outcome and get something which is actually negatively curved. And that's what Charney and Davis proved, together with how to get this kind of construction in higher dimension. Like here, let me just zoom out a little bit. The previous construction was based on a Möbius band. So if you want to do that in higher dimension, just take a higher dimensional version of a Möbius band. The example 2 relies on the construction of this hyperbolic surface having some specific properties, and doing that in higher dimension is not at all trivial. So that's what they did. In dimension higher than 2, they want to construct some hyperbolic manifold that does the same job. So has a system of codimension 1 totally geodesic and orthogonal submanifolds, which you can cut along to get something like the hyperbolizing cell from the example. So something for which the structure of the boundary is somehow similar to the structure of a boundary of a cube. It's not going to be isometric here. In higher dimension, cells in the boundary will have themselves topology. They will be themselves hyperbolic manifolds with boundary and corners. But the poset structure, the structure of inclusions of faces into each other and the symmetries of that is going to be isomorphic as the poset of boundary cells of a standard cube. And something that maybe will come up later, the way to do that is to use some arithmetic constructions. I don't need much about that in my talk, so I'm just going to leave it there. But that's how they construct the hyperbolizing cell in higher dimension. And this is what they can prove about that. So they prove that in any dimension, there's one of these hyperbolization procedures that relies on this construction of this lattice in SON1. So I'm going to denote the hyperbolization by x goes to x gamma with a bunch of properties. Let me highlight the relevant things. So if you input something which is cut 0 or locally cut 0, so your input cubical complex does not have any positive curvature anywhere, then the result space is cut -1 or locally cut -1. So it's really a procedure that brings you from non-positive curvature to strictly negative curvature. Same curvature condition on the fundamental group. You get a cut -1 group, which is in particular gram of hyperbolic. Something nice about this construction is that it preserves links of subcomplexes. So in particular, it gives you a way of constructing manifolds. You input a manifold of non-positive curvature, you get a manifold of negative curvature. And moreover, there's some control of what happens on cohomology. If you have some cohomology classes in the original complex which don't vanish, then you bring them forward to the hyperbolized complex. So you can construct interesting things, keeping track of cohomology. I want to give you a quick list of applications of things that this procedure has been used for, unless there are questions on the construction. We should pause a second here. If not,
no, I think so far it's great.
Okay.
No questions.
All right. So these applications are supposed to answer the naive question of how wild negative curvature can be in higher dimension, going back to this idea that in low dimension, negative curvature is essentially hyperbolic, but that's not true in higher dimension. So the first result is actually by Charney and Davis themselves. They proved that given any triangulable manifold, there is another triangulable manifold n with negative curvature and cobordant to the original manifold. And the idea, at least, of the proof is very simple, so I wanted to sketch that. So you start with your manifold M, and you take the cone over that manifold. So you have some V naught, and this is supposed to be the cone over M. So if M has some given triangulation, then the cone over M will have some given triangulation to that, some cellular structure, and then you're going to hyperbolize that. Let me call the cone over M Cm. I'm going to take the hyperbolization of that space, of that complex. So this is C sub M hyperbolized. So corresponding to the left boundary, you will have some manifold N, which is like what you get if you hyperbolize just M. And then this property that links are preserved by this construction tells you that if you look at the link here, this is a copy of M because it's just the link of the cone point in the cone. That's isomorphic to the space you're taking the cone off. And that's going to be preserved after hyperbolization. So here you still have a copy of M. And then you just go ahead and delete the cone point. So this gives you a cobordism between M and some manifold N, which will be of negative curvature. And I'm cheating a little bit here because I'm looking at triangulable manifolds and I'm not checking all the hypotheses, but that's kind of the idea of what the construction does. Another application is due to Ontaneda, and is the construction of wild manifolds of negative curvature. What I mean by wild here, this is something that works as follows. So it's in higher dimension, and then for any epsilon bigger than 0, Ontaneda constructs a Riemannian manifold with sectional curvatures as close as you want to -1. So pinched negative curvature, close as you want to -1, which are not quotients of hyperbolic space. These are not hyperbolic manifolds. And so these two results together are saying negative curvature is kind of all over the place if you think of things up to cobordism, but most negative curvature is not hyperbolic because there's a lot of negative curvature accumulating to -1, which is not hyperbolic curvature. Different phenomenon from the world of positive curvature. Another result due to Davis and Januszkiewicz. These are again some exotic manifolds. So this is a smooth manifold of negative curvature. Universal cover is a Euclidean space, but the visual boundary at infinity, so what you get if you extend your geodesics all the way to infinity, is not a topological sphere, which means that the metric that you get on this manifold is not equivalent to a smooth metric, meaning Riemannian metric, or to a piecewise linear metric. It's a singular topological metric, which is what you get out of hyperbolization. So our contribution to these kinds of applications is to say that in all these examples and whatever other example people have obtained on these things with strict hyperbolization, you can choose the pathological manifold, the exotic manifold, so that the fundamental group is a subgroup of matrices over the integers, actually sits inside some right-angled darting group. I should also mention that same construction, strict hyperbolization, has also been used recently by Bailiu to do something kind of in the opposite direction. Instead of looking at weird negative curvature, she has results that construct new classical hyperbolic groups of hyperbolic isometries in the classical sense, but it's kind of in a different direction. Yeah, so let me say maybe how we get this embedding of the fundamental group into matrices. What we use is a procedure called cubulation. So a cubulation for a group is an action of your group on a cat-zero cube complex. So a cat-zero cube complex is, again, something like this in the picture, a bunch of cubes glued together, so that when you have many of them coming together at a vertex, the link has to be large. You don't want to create corners of positive curvature. Main characters in the study of cubical complexes, cat-zero cubical complexes, are what are called hyperplanes. So a hyperplane is essentially what you get if you walk straight in your cube complex. Say, want to start from here, I'm inside this two-dimensional square, and I want to walk straight. I want to walk to the opposite face. So that is a canonical way of doing that. And then I'm here in this new square, and I want to walk straight. That's a canonical way of doing that. And then you just keep going. So here, this is a three-dimensional cube, so I'm going to fill in with a square instead of filling in just the boundary. I go through the three-dimensional space, and then I'm here, just keep going through. There's a square in the back. There's another cube in the front. I'm going to fill that in. And then in the back, there's a square, and then here there's a square, and maybe it keeps going. Okay, so it's a way of cutting the complex into two components, the thing above you and the thing below you, in a way that walks straight through every cube. Okay, and every time you sit in a cube and you choose a way to walk, well, you get a hyperplane. Just gonna add some more here, and so on. And what happens is that when you're working with a cat-zero cube complex, hyperplanes are really well behaved. They're organized very well. Just some things that they don't do, they don't display features of positive curvature in any sense. So you don't see a hyperplane that wraps around like that self-intersects essentially. You don't see a hyperplane whose normal bundle is twisted. You don't see that. You don't see a hyperplane that goes away and then comes back. That's like a bulging situation. You don't see that. And you don't see a hyperplane, a couple of hyperplane that behaves like that, meaning they intersect and then start diverging, but then come back together. You also do not see that. These are all things that could happen in positive curvature, but I'm looking at the cat-zero cube complex, so I don't see any of that because I don't want to see positive curvature. Now, why am I focusing on these specific pathologies to forbid? Well, that's what the theory does. If you have something that does that, I'm going to call it special. So a cubulation of a group, so an action of a group on a cube complex is special if when you take the quotient, you don't wrap up the hyperplanes too much. So in the quotient, you don't want to see any of these four pathologies. Well, in that situation, we can consider the following construction. And this is where right angular Artin groups come into the picture. So let me start by constructing this complex sigma, which is the intersection complex for the family of hyperplanes. So here, the two pictures are supposed to be the baby example of Z2 acting on E2. And so this local picture here is supposed to be a piece of the Euclidean plane with a standard cubulation given by integer points. So the construction of the complex is as follows. I start with just one vertex, call it V naught. And then every time I have a hyperplane, I attach an edge and make a loop based at that vertex. So here's another hyperplane, H2, and I'm going to put another loop, E2. And then whenever I have two hyperplanes that intersect, like here, I'm going to glue in a two-dimensional cell in the shape of a torus. Really pretty similar to how you construct a torus out of a square. Just the point of view is that instead of focusing on the edges, I'm focusing on the hyperplanes going through that square. And now if I have another hyperplane somewhere, I'm going to add another loop. And if that hyperplane intersects one of these, I'm going to glue in another torus, and I just keep going. So this is going to end up being a bunch of tori glued together along subtori. So it's a pretty decent cellular complex. And it comes with a map from Y sub G, or Y mod G. So here I was starting with G acting on a complex, and then looking at the quotient. What I do is all the vertices in the quotient, I send them to V naught. And then if I have an edge, like this one, that edge will be crossed by a hyperplane. And I'm going to send that edge to the dual loop on the right. So that's true for a bunch of edges. Yes.
I'm not sure if it's only me, but I see your slide like frozen. I'm not seeing any.
Oh, it's frozen.
Writing.
Thank you. Let me stop sharing maybe and resharing. Thank you for that. That was a very bad moment for the slide to freeze. Looks like one of my devices is not connected to the Wi-Fi. Just give me a second. All right, did it come back?
Yeah, now we see it.
All right.
I think we will have.
Thank you for catching that. Yeah, so let me go back, maybe rewind.
We haven't seen what you drawn. I mean, while you were defining this map phi, so maybe you could
the phi. Okay.
that again, please.
Yeah, yeah. But the construction of the complex sigma was visible.
Yeah, until the torus, it was visible.
Okay. Yes. Yeah. So I was saying that here, to every hyperplane, you associate a loop, and when hyperplanes cross, you glue in a torus. So the complex ends up being a bunch of tori glued together. And the map is the map that sends all vertices to the only vertex you have in the complex. And then when you want to look at edges, if you have an edge, like here I'm highlighting two red edges, they're crossed by H1. So I'm going to send these edges to E1, so highly non-injective. And same if you have a horizontal edge that crosses H2, so I'm going to call that the blue edge, that goes to E2. And again, every time you have an edge crossed by a hyperplane, it goes to the dual loop in the complex. And then essentially those four conditions of what hyperplanes are not allowed to do are pretty much the conditions you need to say that this naive association extends to a map to the entire complex. So I'm going to say special implies that phi extends to a well-defined map on the entire complex. So squares go to two-dimensional tori, cubes go to three-dimensional tori, and higher dimensional things also follows. And you also get that phi is a local isometry. So a geometrically meaningful way of sending Y mod G into this complex of tori. So just to wrap up, that's how you get that if you have an action on a cube complex which is decent, you get the induced maps on fundamental group, which is an embedding in a right-angled darting group. Which I don't need to write down the definition for that. Let me just say that this kind of group is a bunch of Z to the K. So if you're comfortable with bunch of tori glued together, the algebraic version of that is a bunch of ZKs, they're fundamental groups, glued together in a certain way. It's a fairly simple group to study, and in particular, it turns out to be always inside some group of matrices over the integers. So that's the machinery that produces an embedding inside GLNZ. And I should say that this kind of machinery has been used in dimension 3, among other applications, but in particular in dimension 3, work of Haglund, Haglund-Wise, Agel, that gives a solution to the virtual Haken and virtual fibering conjecture. And so we were hopeful to make the same thing work in our setting, right? So if we take a group, which is the fundamental group of one of these hyperbolized complexes, so something like this octopus thing over here. We want to try and make it act on a cat zero cube complex and then check that the action is special, is decent enough so that you can get the embedding in GLZ. So part A, we did that pretty much by hand. So I'll be able to tell you what the complex is. Part B is more technical and we use machinery for that. So I won't go into details about part B. Maybe let me say, before we go into the details of part A, why this approach might work or why it might not work. So it should work because strict hyperbolization starts with X a cubical complex of non-positive curvature. So you have, really when you start the construction, you have a complex which has a lot of hyperplanes, right? Because that's what a cat zero cube complex does. It does have a lot of good hyperplanes. So there's some hyperplane geometry coming from there. However, when you do a strict hyperbolization, you go in every single square and you destroy the cubical geometry, right? That's essentially what the construction does. You start with something that has this canonical version of crossing from side to side, and then you remove the two-dimensional square and you replace that with some weird hyperbolic manifold. So when you go in from a side, you don't quite know what to do, right? Because it doesn't really make sense to say that you walk parallel to the boundary. Parallel is not a good thing in hyperbolic geometry. So you don't quite know how to extend germs of geodesics from one boundary in a decent way, in a meaningful way. On the left-hand side, again, on the column of why this should work, something I've been hiding a little bit is the fact that the hyperbolizing cell from strict hyperbolization comes from arithmetic methods. And whatever arithmetic hyperbolic manifolds are, they are very rich in terms of codimension 1 submanifolds. That's something that arithmeticity gives you. So inside every single hyperbolizing cell, you actually do have a lot of codimension 1 things that are trying to look like hyperplanes. Over to the right, so the column of why this should not work is what happens when you don't have just one cell, but you have several cells in your complex, right? So my complex, like here, has a strip of squares, one after the other. I'm gluing these genus 1 surfaces one next to the other. And if I start with one of these arithmetic hyperplanes in one cell, then what do I do to go over to the next cell? Well, I could take a geodesic extension, just complete the geodesics, but maybe that hits the boundary not going across, but maybe exits the cell in a phase that I'm not interested in. So maybe I will not do that. Maybe I can reflect the hyperplane. As I was suggesting, one of the main features of these hyperbolizing cells is that the boundary structure is really the same as a cube, and in particular, it comes with the symmetries of a cube. So it does make sense to say reflect across one of these faces. So I can go and do that and reflect. And then when I get to the next one, again, reflect. So that's something I can do. But the warning here is that there are spikes, right? Here you don't get something totally geodesic. There are angles. So you don't get something as nice as a hyperplane, which is a convex subspace. These subspaces are not convex, not even quasi-convex. So there's a tension between why the idea should work and why the idea should not work. We think it does work, and let me try and convince you that it can be made to work if you throw in some extra assumption, which is foldability. So I'm going to input complexes in the procedure, which are not just locally cat zero, but also foldable. And foldable means what it sounds like it means. It means that you can fold the complex down to a cube. So these are some pictures, like the one on the left. You can fold it across this line, and you get to 2 squares, and then you fold it across this line, and you get 1 square. Same over to the right. You can fold it across this line, and then again fold it across those 2 edges. You can just fold it down, like you should think about it as having like a napkin, a paper thing, and you can actually fold it down on your desk. The one in the center is not foldable, right? If you try and fold it across this line, you see that you actually have to bend 1 square along a diagonal. And so that's not injective on that cell. So that's not foldable. You can think about this foldability condition as being a condition on the length of links, right? In these examples, the link of the central vertex has to be even for the complex to be foldable. Let me skip over that. Why are we interested in foldability? When you have a foldable complex, we do get some subspaces that can take the place of hyperplanes. So for instance, here is the sequence of maps that we look at. So if X is a foldable complex, this is the folding map. The map G is a collapse map. So you see picture, every space is written above its own picture. So this is a picture of the hyperbolized complex. The collapse map is just killing all the genus, killing all the topology inside each face. It's like de-hyperbolizing, going back to the original square. And then the last map is the universal covering map. So a mirror is what you get if you start with a codimension 1 face and just pull it back along the sequence of maps. So inside the cube complex, this is what you get. Inside the hyperbolized complex, this is what you get. And inside the universal cover, this is what you get. Oops. And it branches out in a sort of tree-like structure. And so on. Okay, so essentially take the preimage of a codimension 1 face and extend it to a maximal subspace. So facts about these subspaces, they are locally convex and locally separating at every stage. So in particular, when you go all the way up to the universal cover, you get something which is globally convex and globally separating. So they behave like hyperplanes in a cat-zero cube complex, even if you are in this universal cover of this hyperbolized complex, which is not a cat-zero cube complex. The collection of mirrors also cuts the space into cells. So let me just sketch what that looks like. So still under the assumption of foldability, same sequence of maps and spaces. And I'm going to take the preimage of an open cell, for instance, the open 2 cell here, and I pull it back. I get an open 2 cell here. I get an open 2 cell here. And then all the way up to the universal cover, I get this region in the universal cover. Well, these are not quite cells in the universal cover because this is not something with compact closure. So this is not a cellular structure on the nose, but it's good enough to define a dual cube complex. So this is the definition of the cube complex that we're going to be interested in. So again, here on the right is a sketch of what the universal cover of this hyperbolized complex looks like. And here, vertices are 0 cells, pieces of the mirror are 1 cells, and then the thing I just defined, the yellow thing over here was the 2 cell. So that's the kind of generalized cellular structure I find on my universal cover. And I define a dual complex by taking the dual complex, essentially. So I'm going to take a vertex for each cell. So this is the thing I'm doing in red. So there's a 0 cell, a 1 cell, a 2 cell, and a 1 cell here. I put an edge only for codimension 1 inclusion. So 0 is contained in 1, 0 is contained in 1, and 1 is contained in 2, 1 is contained in 2. But I'm not going to put something between 0 and 2, as you would do when you do barycentric subdivision. So I'm dropping that edge over here. So that gives me a graph, and then I throw in cubes every time I see a cube. Okay, so here, this 2-dimensional part is going to give me a square in my dual cube complex. And this is what we proved about this complex. So again, under the hypothesis that it's locally cat-zero and foldable, this dual cube complex turns out to be a cat-zero cubical complex. So that's how we recover cubical geometry out of a strictly hyperbolized space. And we do have an action of the fundamental group on this cat-zero cube complex. So this is looking like a cubulation for the group. I should point out that this complex here is not locally finite, and that this action here is not proper. So not quite a cubulation on the nose. There's a lot of failure of compactness going on. But the good thing about this this dual cube complex is that we can read off what the stabilizers look like. And so that is good enough for us to work with it. And corollary of this theorem, together with some technology developed by other people, is that the fundamental group turns out to be a special group. So it does have a special action on some cube complex. And as a result, it sits inside the right angle arcing group and eventually inside the general linear group over Z. And I think I'm right on time, so let me skip some details and just thank you for your attention.
Okay, thank you very much, Lorenzo, for your beautiful talk. So maybe let's unmute ourselves and thank Lorenzo. Is there any question? I do have one actually. On this very last slide that you showed, just this dual, so this C of X gamma tilde,
This guy.
dual, yeah, exactly. What do you know about its global geometry, like its rough curvature or?
Yeah, it's globally cut zero. It's simply connected.
Okay.
Links are very large, so it's contractible.
Okay.
The dimension is the same as the dimension of the original complex. So really the only bad thing it does is that it's not locally finite.
Okay, and what do you gain compared to the, before taking the dual? I mean,
like with respect to this one?
yeah, I mean, you took this dual. I'm a little lost in actually why do you need to take this dual?
Right. Let me scroll back up to this point. So this is essentially the key sequence of spaces. So this is the complex that I input in the the strict hyperbolization. It's like some given complex, which does not have negative curvature necessarily. It's like non-positive curvature. And then hyperbolization gives you this negatively curved space.
Yeah.
So going from X to X gamma, that's how you create something of negative curvature.
Yes.
But once you do that, you have completely destroyed the cubical geometry inside. So you do not know if the fundamental group of X gamma, which is this new negatively curved group, you don't know if that guy has an action on a cubical complex.
I see.
So this is essentially our way of constructing a cubical complex on which that group acts. Go up to the universal cover, do something that introduces some collection of subspaces that cuts the universal cover into chunks, and then take a dual combinatorial structure to that. That turns out to be a cut zero cube complex.
Mm-hmm.
And that's what the fundamental group of this space acts on.
Okay, so just to summarize, X, the universal cover before taking the dual, the universal cover was still cut zero.
Correct. The universal cover of X is a cut zero cube complex.
Yeah, okay. But
it does not have an action of this group.
I see. Okay,
Correct.
I understand. Okay.
Correct. Yeah.
Thanks. And are there other questions? If not, maybe I would be happy to ask Lorenzo to go through his last slide, because everything was very interesting and you actually took 5 minutes less than necessary, so less than 1 hour. So if you don't mind.
Oh, the last slide is one?
Yeah, it would be nice to listen to the part that you skipped since.
Oh, sure.
Technically, you have 5 more minutes.
Okay. Well, one was just a quick thing on one of the main technical tools that we use in the study of this dual cube complex is the existence of what we call a height function. So it's something defined on vertices of the cube complex valued in 0, 1, n. So just in the picture, maybe it's easier to follow. So this is a sketch of the universal cover of X gamma, and I'm superimposing this dual cubulation. And some vertices come from 0 cells, some vertices come from 1 cell, some vertices come from 2 cells. So I'm just keeping track of what the vertex corresponds to. And that's what I call the height function. And that's how we think about the complex. Just don't think about the complex as laying down on X gamma. Think of it as picking up the highest dimensional vertex. So in this picture, I'm picking up the red vertex labeled by 2, and I'm pulling it up and letting things fall down according to the dimension. So it's kind of a Morse function on the cube complex. So it gives you like the composition into level sets. And that's good because that highlights the combinatorial geometry of the complex. For instance, links are bipartite, which is something we can see here. If I take this vertex, there's a clear distinction between directions that go up and directions that go down. So that's something we can use to study links of points in cells. And it also gives you a way of pulling paths to their efficient, say, representative. Like if I have something that starts from here, goes down, up, up, and then down, down, up, something like that, I can just pull it straight, imposing that it goes up as fast as possible and then down as fast as possible, keeping like an efficient trajectory with respect to this height function. And those are the two technical tools to see that the complex is locally cut zero and then globally simply connected. And together that gives you cut zero. Yeah, that's what I had on the slide. Thanks.
Thank you very much. So I would propose to thank Lorenzo again, unless there are other questions. Let's unmute again, and thanks, Lorenzo.
Thank you.
All right. Thank you very much for your great talk. I'll stop recording now.